Hello, and greetings from the Department of Mechanical Engineering, University Malaya. We are FloodGuard Technologies, a team dedicated to developing innovative drone solutions for flood rescue operations. Today, we are excited to present our AI-assisted flood rescue drone project. But first, let us introduce the team behind this innovation.
First, we have Tan Sun Seng, our team leader and AI engineer. Next is Eugene Angsusei, serving as the mechanical engineer. Finally, we have Phi Xian, who is our system engineer.
To begin, let us first understand the problem we aim to solve. Flooding has become one of the most frequent and devastating natural disasters in Malaysia, driven by climate change, rapid urbanization, and increasingly unpredictable weather patterns. Today, nearly 9% of Malaysia's land is flood-prone, affecting approximately 4.9 million people every year and causing an estimated RM1.27 billion in annual economic losses. Beyond the economic impact, floods often leave victims stranded in isolated areas where access by conventional rescue teams becomes extremely difficult. The delivery of life-saving emergency supplies is frequently delayed, while rescuers must navigate dangerous floodwaters, strong currents, and poor visibility under severe time pressure. Traditional search and rescue operations also rely heavily on manual observation, making it challenging to locate victims quickly across large disaster zones.
The problem we are trying to solve is regarding flood natural disaster, whereby we have identified three main challenges. First is victim detection limitations. Second is the lack of situational intelligence amongst the rescue team. And third being the delayed emergency aid delivery to the victim. And our team have developed the corresponding solutions to tackle these issues.
During flood disasters, every second matters. Traditional search operations rely heavily on manual observation, causing delays in victim localization and rescue coordination. To solve this problem, we developed Aero Command, an AI-powered aerial rescue coordination system. Our drone platform integrates a custom payload mechanism, dual-axis camera gimbal, and Jetson Nano Edge AI computer for real-time detection, clustering, and coordinate estimation. The operator starts the live stream, and the onboard YOLO-VATE model immediately performs real-time victim detection from aerial footage. After detection, the system applies DBSCAN clustering to automatically group nearby victims based on spatial density. Using live telemetry, camera geometry, and altitude projection, the system converts image detections into real-world GPS coordinates. Each victim group is then transformed into mission-ready waypoints. Generated waypoint files are fully compatible with Mission Planner and Q-Ground Control for autonomous drone navigation. The drone can automatically navigate to multiple victim groups for emergency payload delivery. Aero Command also integrates a real-time cloud coordination platform powered by Supabase. All missions, telemetry, victim groups, and rescue team updates are synchronized live across connected operators. Ground rescue teams can claim missions, update victim status, and coordinate operations collaboratively in real time. To verify the system, we conducted 3 field tests using real drone flights. The AI successfully generated 11 mission waypoints with a 100% success rate. All generated coordinates remain below a 10% geolocation error threshold, with an average error of approximately 2.6 meters. Most importantly, the drone successfully navigated to the generated coordinates and delivered life jackets to the intended target locations, validating the complete end-to-end rescue workflow. These results demonstrate that the complete workflow, from AI detection and clustering to GPS estimation, mission generation, and autonomous payload delivery, is fully functional under real flight conditions.
First, we set up the drones by installing the ETE-026 GPS modules and powering on the entire system. An RGB camera is mounted on a custom-designed 2-axis gimbal, allowing both yaw and pitch rotation. ETE-026 GPS module, Jetson Nano, and RGB camera are all properly connected and communicating with each other. The real-time image footage and telemetry data are transmitted to the Jetson Nano for onboard AI processing. all the results being transmitted to the laptop backend server where the DBSCAN clustering algorithm performs victim grouping and GPS coordinate estimation. The process results are displayed on the Aero Command web desktop. At the same time, all the results are synchronized with the Supabase cloud database for storage and multi-user access. After the clustering process is completed, the backend automatically generates a QGC waypoint mission file. The file is uploaded to the Cube Flight Controller through UDP connection. Finally, during autonomous flight, the Cube Flight Controller communicates with the Arduino Uno to control the relay and servo motor to activate the payload release mechanism.
Now, let us introduce the ins and outs of our payload mechanism. First, our custom-made package box is capable of storing up to 8 emergency items, including life jackets, communication devices, food supplies, and medical kits. The box also features a dedicated electrical access hole, allowing wiring to pass through conveniently for cleaner and more organized circuit management. In addition, both the front and rear panels feature a curved aerodynamic design to reduce drag acting on the package box during flight. As you can see from the comparison between the maximum drag force acting on the payload mechanism of the curved and flat surface, whereby the drag force acting on the design with a flat surface is much larger. We also conducted flow simulations for our fully assembled prototype with the drone and compared our design with a conventional payload configuration of similar size. The results show that our streamlined payload mechanism reduces aerodynamic drag, allowing the drone to maintain more stable flight at higher speeds and operating altitudes while improving resistance to wind disturbances. Lower drag also reduces the aerodynamic load acting on the UAV, enabling a greater proportion of the available thrust to be utilized for carrying emergency payloads rather than overcoming air resistance. The front panel houses our dual-axis camera gimbal, while the rear panel also functions as a compartment for the electrical components. For the payload release mechanism, we utilize a rack and pinion system. When the gear rotates, the hatch slides open, allowing the payload to be released smoothly from the box. Here is how the full assembly looks when attached to the drone. Our custom attachment bracket features a modular design, enabling the payload mechanism to be adapted onto different drone platforms with minimal modifications. Overall, the payload mechanism combines compactness, modularity, and reliable payload deployment into a practical system designed specifically for flood rescue operations.
The Cube Flight Controller handles autonomous navigation using the waypoint mission generated by our AI system. The Arduino Uno communicate with Cube Flight Controller using UART serial to control 6MG996R servos and relay modules to release life jackets or emergency supplies at the designated waypoints. A dedicated 6-volt 10-ampere UBEC powers the servos, ensuring reliable and stable operation during rescue missions.
We have identified some benefits that our project can provide, particularly for the public and rescue teams. As for the value to the public, our project can have faster victim discovery, quicker aid delivery, safer evacuation decisions, as well as better survival odds. On the other hand, our project can also benefit the rescue team by having less manual searching, prioritized group missions, shared live map and status, and finally to have safe and clearer decisions.